Everything you are told about the beginning of the universe is missing a chapter. Not wrong, not a lie, just incomplete. Like being handed a book that starts on page 3 and never being told pages 1 and 2 even existed. The Big Bang happened. That part is real. 13.8 billion years ago, the universe was unimaginably hot, impossibly dense, and it expanded. We have the evidence, we have the math, we can see the afterglow of that moment right now, in every direction we point a telescope. A faint hiss of ancient light still washing over the earth from 380,000 years after the beginning. But here's what nobody told you in school. The Big Bang was not the start of the universe. It was the result of something else, something that came before it. Something so extreme, so strange, and so poorly understood that physicists have been arguing about it for decades. And the argument isn't over. The real beginning of everything didn't look like an explosion. It looked like nothing we have a word for. And the deeper you go into what actually happened, the stranger it gets. What we think we know. Most people carry the same mental image of the Big Bang, a single point, infinite density, and then explosion. Everything bursting outward from nothing into something. Space itself stretching, time itself starting. The whole universe born in a single catastrophic moment 13.8 billion years ago. It's a clean story. It fits on a poster. And it's been repeated so many times by so many textbooks and documentaries and museum placards that it feels like settled fact. But there's a problem hiding inside that story. A problem so fundamental that once you see it, you can't unsee it. If the Big Bang was the beginning of everything, the beginning of space, the beginning of time, the beginning of matter and energy and the laws of physics themselves, then you cannot ask what caused it. There is no before. The question doesn't have meaning. Time didn't exist yet for a before to happen inside. For a long time, that answer satisfied people. Even Stephen Hawking famously compared asking what came before the Big Bang to asking what's south of the South Pole. The question sounds valid, but the geography makes it meaningless. And for about 50 years, that was roughly where things stood. Then, in 1979, a young physicist named Alan Guth sat down with a problem. Not the question of what came before the Big Bang. He wasn't thinking that big yet. He was thinking about something much more specific. He was thinking about why the universe is so flat. Here's the issue. When you look at the universe on the largest scales, and we can now see it across billions of light years, it's almost perfectly uniform. The temperature of space is essentially the same in every direction. The density of matter is distributed with eerie evenness. The geometry of space itself is flat, almost mathematically perfect. This is strange, deeply strange, because the Big Bang, as originally conceived, gives us no reason for any of that. Think about it this way. If you detonate a bomb in a room, the shock wave doesn't travel outward perfectly. It creates hotspots and cold patches. Density varies. The explosion is chaotic. And the Big Bang, in the original model, should have been incomparably more chaotic than any bomb, the most violent event in the history of existence. So why does the universe look like it was ironed flat? Why do two opposite sides of the observable universe, separated by 90 billion light years and physically incapable of ever having interacted, have virtually identical temperatures? This is called the horizon problem. And in 1979, Alan Guth found the answer. But the answer didn't just solve the problem. It rewrote the entire story of how the universe began. Inflation, the real bang. What Guth proposed is called cosmic inflation. And the first time most people hear the details, their reaction is something between disbelief and vertigo. Here is what inflation says happened before the Big Bang, or more precisely, what happened instead of what we call the Big Bang. In the first unimaginable fraction of a second after time began, the universe was not expanding slowly. It was not filled with the particles and radiation that would eventually become stars and galaxies. Instead, it was filled with something physicists call the inflaton field, a type of energy so strange it acted like anti-gravity. Instead of pulling inward, it pushed outward, exponentially, catastrophically, in approximately a trillionth of a trillionth of a trillionth of a second, a span of time so brief it makes a microsecond look like an eternity. The universe expanded by a factor of 10 to the power of 30. Let that sit for a moment. A single bacterium expanding to the size of the Milky Way, then expanding to the size of the Milky Way again, then again, 30 times over, in a moment so short it has no name in human language. This is inflation, and it explains everything the original Big Bang model couldn't. The flatness problem? Solved. When you inflate something by that factor, any curvature becomes negligible, the same way the surface of the Earth looks flat to you even though it's a sphere. Inflate it enough, and it looks perfectly flat from where you're standing. The horizon problem? Solved. The distant regions of the universe that look identical weren't always separated by 90 billion light years. Before inflation, they were in contact. They had time to reach the same temperature, the same density, the same conditions. Then, inflation stretched the space between them so fast that by the time it ended, they were impossibly far apart, but still carrying the same imprint from when they were neighbors. But here's the part that should genuinely unsettle you. Inflation didn't just solve those problems. It accidentally explained something far more important, something that nobody expected. It explained why there's anything at all. Before inflation ended, the universe was essentially empty. The inflaton field filled space, but there were no particles, no matter, no light. Just this strange, expanding energy, stretching space in every direction at speeds that make the speed of light look slow. But quantum mechanics, the physics of the very small, says that nothing can be perfectly smooth. At the smallest scales, reality is fundamentally fuzzy. Space itself has what physicists call quantum fluctuations, tiny random variations in energy density that are baked into the fabric of existence. Normally, those fluctuations are microscopic, subatomic, invisible. But inflation stretched them. Every quantum ripple, every infinitesimal bump and valley in the energy density of the early universe was magnified by inflation from scales smaller than an atom to scales larger than galaxies. These fluctuations became the seeds of everything. The slightly denser patches of energy became regions where matter would eventually clump together. The slightly less dense patches became the vast empty voids between galaxy clusters. The large-scale structure of the entire observable universe, every galaxy, every star, every planet, including this one, is a direct imprint of quantum noise from the first incomprehensible fraction of a second of existence. You are the result of quantum static, blown up to cosmic scales by an inflation event 13.8 billion years ago. And then, inflation ended. When the inflaton field finally decayed, all that energy had to go somewhere. It was converted, dumped into space as an unimaginably hot, dense bath of particles and radiation. Quarks and electrons and photons, flooding the universe at temperatures exceeding 10 trillion degrees. That moment, that conversion, is what we call the Big Bang. Not the beginning, the aftermath. What was there before inflation? So if inflation came before the Big Bang, the natural question is, what came before inflation? And this is where the story stops being settled science and starts becoming one of the most contested frontiers in physics. Alan Guth, the man who invented inflation, now believes the universe may be eternal. Not just old, eternal. As in, it has always existed and will always exist in some form. His reasoning is counterintuitive but elegant. If inflation is driven by a field of energy, and that field exists in space, then there's no particular reason for inflation to stop everywhere at once. In some regions, inflation would end, creating a pocket universe like ours, filled with matter and light and the physics we recognize. But in other regions, inflation would continue. And those regions would keep expanding, keep inflating, keep spawning new pocket universes, eternally. This is called eternal inflation. And if it's correct, our universe is one bubble in an infinite, ever-expanding foam of universes, each one born from a tiny region where inflation happened to end. Each one potentially governed by slightly different laws of physics, each one utterly unreachable from any other. This is the multiverse. Not as a science fiction concept, but as a direct mathematical consequence of the most successful theory of cosmological origins we have. And Guth's collaborator Sean Carroll takes it further. He argues that if the universe is truly eternal and entropy, disorder, always increases over time, then what we experience as the past is simply the direction of lower entropy, and the universe extends infinitely in both directions. There is no beginning. There is no end. There is just an eternal cosmos, and we happen to exist inside a brief, improbable, low-entropy window of it. But eternal inflation is not the only alternative on the table, and it's not even the strangest one. Some physicists argue for a cyclic universe, a cosmos that doesn't expand forever, but eventually contracts back on itself in what they call a big crunch, then rebounds into a new Big Bang. Roger Penrose, one of the greatest mathematical physicists alive, has proposed a specific version of this he calls conformal cyclic cosmology, a model in which our universe is simply the latest in an infinite series of universes, each one beginning in a Big Bang and ending as a cold, empty expanse of radiation, which then becomes the initial conditions for the next cycle. Penrose believes he's found evidence for this in the cosmic microwave background, the faint light left over from our own Big Bang. He claims to see concentric rings of slightly different temperature, which he argues are echoes of massive black hole collisions from a previous universe, leaving their gravitational imprint on the fabric of our own. Most cosmologists are skeptical. The statistical evidence is disputed. But the idea itself, that our Big Bang was not a beginning, but a bounce, is taken seriously enough that multiple research groups are actively trying to test it. And then there's the most unsettling possibility of all. In 2025, researchers published a paper in the journal Living Reviews in Relativity, arguing that we've been asking the question wrong. We've been trying to solve Einstein's equations analytically, with pencil and paper, finding exact solutions. But those solutions require assumptions about the universe that may not have held true near the Big Bang. The universe, during inflation, may have been chaotic, uneven, fundamentally different from the smooth, homogeneous cosmos we live in today. To probe those conditions, they argue, we need numerical relativity, supercomputer simulations capable of solving Einstein's equations in messy, non-symmetric spacetimes. The same techniques used to model colliding black holes. The same tools that first predicted what gravitational waves should look like, decades before we could detect them. The implication is striking. We may not yet have the mathematical tools to know what happened before inflation, but we're building them. And what those simulations find in the next decade or two may force us to rewrite the story of the beginning yet again. Here is the deepest problem of all. There is a moment in the early universe called the Planck time. It occurs 10 to the power of negative 43 seconds after the beginning of time. 1/10,000,000th of a trillionth of a trillionth of a trillionth of a second. Before that moment, our physics breaks down entirely. Not because we haven't done the math, but because at the densities and energies that existed before Planck time, quantum mechanics and general relativity, our two most successful theories of physical reality, are both simultaneously required, and they directly contradict each other. We don't have a theory that reconciles them. We don't have equations that work in that regime. The Planck time is not just the earliest moment we've measured. It is a wall, a fundamental limit of our current understanding. What happened before that wall is, at present, literally unknowable using the tools we have. This isn't a gap we expect to fill next year or in 10 years. It may require a complete theory of quantum gravity, uniting the two great pillars of physics that have resisted unification for over a century. String theory attempts it. Loop quantum cosmology attempts it. Neither has been confirmed by experiment. And there's something even stranger hiding in the math. One theorem in inflationary cosmology, the Borde-Guth-Vilenkin theorem, suggests that any universe undergoing inflation cannot be extended backwards in time indefinitely. Even eternal inflation has a beginning of some kind. The universe cannot be truly eternal in the past, only in the future. Which means Even if we accept inflation, even if we accept the multiverse, there was still a first moment, still a point before which there was nothing. Or, as Alan Guth's collaborator Alexander Vilenkin puts it, the universe was most likely created from literally nothing. Not a quantum vacuum, not pre-existing space, nothing. Quantum tunneling from absolute non-existence into the first moment of inflation. That is the most current, most mathematically rigorous answer to the question, what happened before the Big Bang, that physics can currently offer. The universe appeared out of nothing because quantum mechanics doesn't forbid it. What this tells us about ourselves. There's a version of this story that's deeply unsatisfying. We wanted an answer. We wanted to know what came before the Big Bang. And what we found instead was inflation. And before inflation, possibly eternal inflation. And before that, possibly a quantum tunneling from nothing. And before that, a wall, a theorem, a boundary beyond which our physics dissolves into silence. Every answer generates a deeper question. Every layer we peel back reveals a stranger layer beneath it. But I think that's the wrong way to see it, because here's what we've actually accomplished. In roughly 1 century, a single human lifetime, we went from not knowing whether the Milky Way was the entire universe to understanding the large-scale structure of the cosmos across 90 billion light-years. We detected the faint afterglow of the Big Bang. We mapped its temperature fluctuations to 1 part in 100,000. We found in those fluctuations exactly the pattern that inflation predicts: quantum noise stretched to cosmic scales. We have looked at the oldest light in existence and found inside it the fingerprint of something that happened before the universe began. That is not failure. That is one of the most extraordinary things the human mind has ever done. And the frontier is still moving. The James Webb Space Telescope is finding galaxies in the early universe that are too big, too bright, too structured. Galaxies that shouldn't exist so soon after the Big Bang, according to our current models. Something about the early universe is still surprising us. Something about how structure formed, how stars ignited, how matter organized itself in the first hundreds of millions of years is still not right in our models. The story isn't finished. It may never be finished. And that's not a tragedy. That's the whole point. We live on a pale blue dot, orbiting an unremarkable star in a galaxy that is one of at least 2 trillion in the observable universe. Our universe may itself be one of an infinite number, born from an eternal inflation we cannot see beyond. The question of what came before the Big Bang may be unanswerable with human tools, now or possibly ever. And yet we keep asking it. That impulse, the one that makes a species look up at the night sky and refuse to accept "we don't know" as a final answer, is the same impulse that built telescopes and particle accelerators and supercomputer simulations powerful enough to solve Einstein's equations in the chaos of the early cosmos. The universe is under no obligation to make sense to us. It doesn't owe us a clean answer, but we keep looking anyway. Asking for support always feels a little awkward, so I'll keep this brief. These videos take a long time to make. The research, the writing, the visuals, every one of them is an attempt to take something genuinely difficult and make it feel like something you want to stay up until 2 a.m. watching. If that's what this was for you, please consider supporting the channel. The join button is right below the video. You're not just donating, you're buying time. Time to dig deeper, go bigger, and keep exploring the questions that don't have clean answers. And if you want to keep going right now, I think you'll love this one next.